Hello, hello, hello. Hi, everyone. Gonna wait for a few more people to arrive. Greetings. Just had to finish my chapter there of the bookie I was reading. What am I reading? Ham on Rye by Charles Bukowski. It's about an immigrant growing up poor during the Depression in the Los Angeles area, and it's kind of like really funny at some parts and then really depressing at other parts, and I don't know what to make of it. I can't tell if I enjoy reading it or if I hate reading it, but it does kind of have me hooked. Okay. And it's very vulgar, so I would probably not, just beware of that if you decide to read Ham on Rye by Charles Bukowski. Okay, so let's go ahead and get started. I want to remind everyone that your midterm is available today. You can get started on it if you like. It's due next Monday. So the first thing I wanted to talk about today is something called angular kinematics. Okay, and so this lesson is going to be more or less review if you took my class last year. We're not really going to take it that much further than we did last year. So what if we have a rod, something like this, and the rod is making, it's fixed at the end, so it has a pivot point. The rod makes an angle of theta with the horizontal. So we can basically define the orientation of the rod by giving this angle, okay? So theta is called the angular position. Okay? And basically it defines the orientation of an object. For this lesson, and I'll explain why in a moment, we are going to use units of angular position that are radians. Okay, so other valid units of angular position are degrees. Number of rotations is also used, but for this lesson, we are going to use, have I already talked about angular kinematics? I don't think that I did. For this lesson, we are going to use radians, and I'll explain why in a moment. Delta theta is called the angular displacement. So let's say that this rod goes from this position and then it rotates to this position. So like that would be an angular displacement of plus pi over 2 radians. Okay, because it rotated 90 degrees in the counterclockwise sense. If it rotated this way, like that would be an angular displacement of negative pi over 2. Okay? So basically the angular displacement is measuring how much did it rotate. We can define the angular velocity, which is denoted by the Greek letter omega. I didn't draw that very well. This is the Greek letter omega. Omega is the angular velocity, which is defined as the derivative of the angular position with respect to time. And so basically the angular velocity measures the rate of spin. How fast is this thing whirling around? The units of angular velocity are radians per second. Okay. Other valid units of angular velocity are degrees per second, or rotations per second, or rotations per minute. RPM is the unit of angular velocity. But for the purposes of this lesson, we're going to use radians per second. Then there's the Greek letter alpha, which is known as the angular acceleration, which is defined as the derivative of the angular velocity with respect to time. Or you could think about it as the second derivative of the angular position with respect to time. Okay? Units of angular acceleration are radians per second squared. So what is angular acceleration measuring? It's measuring the rate of change of the spin speed. So how quickly is the rate at which it's spinning changing? Okay, so there's obviously a connection between linear quantities versus angular quantities. Okay, so if we think about when we studied linear motion, we had x, which is your linear position. Now we have theta, which is your angular position. We had v, which is defined as the derivative of the linear position. That's your linear velocity. Okay? Omega is the derivative of the angular position, angular velocity. A, the linear acceleration, was the derivative of the velocity with respect to time. So alpha is the derivative of omega with respect to time. So we can see that these, there's a correspondence between linear quantities and angular quantities, okay? Keep in mind when something is rotating, it's rotating about an axis, and so there's a connection between angular motion and one-dimensional linear motion, okay? So you might recall that we learned a couple of kinematics equations. So when the linear acceleration is equal to a constant, okay, and that was important, is that linear acceleration had to be constant. Earlier in the school year and throughout last year, we used these equations. So the three kinematics equations. Okay. So these are the three equations of linear kinematics. Analogously, and I derived these using calculus. I'm not going to show the derivations again because the relationships between the variables are exactly the same. But when alpha, the angular acceleration, is constant, we get three equations of angular kinematics. So all I'm going to do is replace the linear quantities variable with the angular quantities variable. So theta of t equals theta naught plus omega naught t plus 1/2 alpha t squared. We have omega of t is omega naught plus alpha t, and we have omega final squared equals omega initial squared plus 2 alpha delta theta. Okay, so these are the equations of angular kinematics. All right. And you can only use these equations when alpha is constant. All right, so because we've spent so much time studying linear kinematics, I'm not going to do any examples with angular kinematics. All right? Boom. So now I want to talk about, this is the next part of this lesson, Newton's second law for rotations. So it is possible to derive this equation. I'm not going to show the derivation. If you ask me during office hours or something, I could show you. But yeah, one of the things about this equation is that it only applies to rigid, so-called rigid bodies. So what is a rigid body? A rigid body is something that's not flexible, okay? So if I take my calculator is a rigid body. I'm able to hold one end and the shape doesn't change. Shape doesn't change, okay? Its orientation can change, but its shape does not. My phone is a rigid body, okay? Its shape does not change, no matter the orientation. A piece of paper, on the other hand, is not a rigid body because it's flexing and doing different things, and it can move around. So the reason that it has to be a rigid body is because if the shape can change, then the rotational inertia can change. You know, if because remember, rotational inertia depends on distance from the pivot point. So if you have something that's shape can change, its inertia is not a constant, which screws up the derivation. Okay. All right. So if and the other thing I want to say is a rigid body is actually an idealization. There's no such thing as a perfectly rigid body. If I hold this calculator, its shape actually does change a little bit if I change its orientation, because but the amount that it changes is so small that it's negligible. Okay, so if the amount that something flexes when it is moved around is negligible, we could say that for all intents and purposes, it is a rigid body. So if you assume you have a rigid body, okay, then it is possible to show the following law, which is called Newton's second law for rotations. The net torque is equal to the rotational inertia times alpha. Okay? So this is a nice equation because it connects all of the rotational quantities that we've learned about so far, and it puts them into one equation. Okay? So we have torque, which if you recall was F perp times R. We have inertia, which if you recall was sum over m r squared. And then we have alpha, which is the rate of change of angular velocity. So it has all these things. So how is this equation used? Well, most often it's used like this. Well, we would divide both sides by inertia, and that would tell us what the angular acceleration is. And then if that is constant, which it's not always going to be constant, but if it is constant, then we can apply this to angular kinematics. For example, we could find omega of t is omega naught plus alpha t. So now we can plug that alpha into here. All right, and then that's going to allow us to predict the motion. All right, so that's nice. It's a nice little equation. Even if it's not constant, we could still set this equal to, the derivative omega and then integrate it, okay, to get. So we can use this equation in all kinds of different ways. So let's do an example. And I like this example because it's going to put everything together. So let's suppose we have a rod. Okay, the rod is fixed at one end. Here's the ground. Okay. Ooh, I just thought of a really good problem. Is that a good problem? I'm happy now. I thought of a good problem. Okay. So here's the floor. Okay. I'm not going to give it to you guys this year, but if you want a special problem, I'll give you a special problem. Okay. So if you have so it's, let's think about this as being the rod. It's going to have a gravitational torque on it that swings it. Okay. So gravity is trying to swing this thing down. So the gravitational torque acts as if all of the weight were concentrated at the center of mass. So let's say the center of mass is right here. And so you've got a gravitational torque, mg. And this distance right here would be RCM. All right. Then we also have a 500 Newton force that acts at the end of the rod, and it makes an angle of 30 degrees with the vertical. So the rod is 4 meters long with lambda of x equals 3x squared kilograms per meter. Okay? So what we want to do is we want to figure out what is alpha at the instant shown. And that's an important part, at the instant shown. Okay? And I'll come back to that at the end after we've done the example. So what do I need to do to calculate alpha? I need to calculate net torque, and I need to calculate inertia. So maybe I'll calculate inertia first. Why not? So if you recall, inertia was defined as, in its integral form, was defined as x squared times lambda, that integral, with respect to x. Okay? Now, the rod is 4 meters long, so my integral is going to go from 0 to 4. X squared times lambda of x, 3x squared, dx. So this is going to be 3 times the integral from 0 to 4 of x to the 4th dx. So we bump up the power, and then we divide by the bumped up power, and then we plug in 4, we plug in 0, we subtract them. The 0 one just gives 0, so all I have to do is plug in 4. Okay? So this gives a rotational inertia, 3 times 4 to the 5th divided by 5 of 614 kilogram meters squared. So that's the first part. All right? We've got our inertia. Now we have to get the net torque. The net torque is composed of two torques. There's the torque from the applied force, and there's the torque from gravity. So let's go ahead and figure out. The applied torque. All right. The applied torque is going to be F perp times R. F perp is going to be the component of this force that is perpendicular to the line connecting the pivot point to where the force is applied. So this horizontal line, perpendicular to horizontal, is vertical. So this component right here is F perp. And it is adjacent to the angle, this angle right here. So that's going to be cosine. So we have 500 cosine of 30 degrees is F perp. And then it acts at the end of the rod. The rod is 4 meters long, so it would be times 4. So this is the applied torque. And that gives a value of 1,732 Newton meters. And I'm going to put the sign in by hand. We can see that if I push on the rod in that way, if I use my phone as an example, here's the pivot point, I push up, the phone rotates in the counterclockwise sense. So this is a positive torque. So now we have the torque due to gravity that we have to consider. Okay. The torque due to gravity, I gave you an integral expression for the torque due to gravity. It's, one equation I gave you is that it's the perpendicular component of the weight force times RCM. In this case, we can see that RCM and the weight force are perpendicular to each other already. So it's just going to be mg/RCM. All right. I gave you an integral expression for m times RCM. So remember, RCM is the integral of x times lambda over the total mass. So RCM times m would just cancel out the m's, and I just get the integral of x times lambda. So this is just going to be g times the integral of x times lambda. All right. So g is 10. The integral is going to go from 0 to 4 of x times lambda. So this is going to be 30 times the integral from 0 to 4 of x cubed. This is going to be 30 over 4 times 4 to the 4th, which is 1,920 Newton meters. Now, the gravitational torque is going to tend to rotate this rod in the clockwise sense, so it is a negative torque. So now we can calculate the net torque. The net torque is just going to be the sum of the applied torque and the gravitational torque, because those are the only two torques involved. So we have 1,732 minus 1,920. That equals negative 188 Newton meters is the net torque. So I know what the inertia is. I know what the net torque is. So I can calculate alpha is net torque. And by the way, this is a rigid body. It's a rigid rod, so I can apply this equation. Net torque over I. Negative 188 divided by 614 equals negative 0.3 radians per second squared. So that is the angular acceleration of this rod at that particular instant. Okay? So why did I say at that particular instant? That's what I want to talk about, and this will be the last part of my lesson. Okay? What if I have a force that is constant in direction? Okay? If you have a force that is a constant direction, so for example, gravity is constantly pointing downward, as the thing rotates, gravity has a constant direction. But if we think about the vector that goes from the pivot to where the gravitational force is applied, that angle, that vector is rotating as the thing rotates. Okay? So, for example, if we think about this rod, it starts out with gravity acting downward right here. Okay? But then it starts to rotate in the clockwise sense. So now the rod is pointed this direction. Gravity acts from the same location, and it points in the same direction. Okay? If we look here, what is the angle between R and the gravitational force at that instant? Here we have this angle is 90 degrees. Okay? Here we have that F perp This is F perp. So see how now we don't have that the angle is 90 degrees. Now we have to do trig. Okay? What about when the thing is vertical? If the thing is vertical, then gravity points this way, and F perp is 0 because it's parallel to R. Okay? So the reason why I say at that instant is because as the object rotates, F perp changes. So torque is not constant, which means that the angular acceleration is not constant. Okay, so that's an important point for this particular example. So anytime you have forces that are maintaining their direction, even as the object rotates, you are going to have alpha not equal to a constant. So that's an important thing to understand. Okay. What if I wanted to apply a constant torque to this thing? Well, if I just kept my force going upward and I push it upward, see, eventually I just lose contact with it. Okay. But what I would have to do if I wanted to exert a constant torque is, as the thing rotates, the force also rotates with it. See how I'm always keeping my force perpendicular to the calculator. All right. So if you have a force that's acting like that, where it's sort of chasing the object around as it rotates, then you can have a constant angular acceleration. So could we use the equations of angular kinematics in this particular example? No, because to use the equations of angular kinematics, alpha must be constant, but in this example, alpha is not constant. All right, so that is my lesson for today, and I will see you in the Zoom room.